Now let's look at a problem that's a little bit tougher. Let's see if we can find the double integral over r of x dA, where r is the region in the xy plane inside the circle x squared plus y squared equals 8, and to the right of the line x equals 2. You might recall that we've looked at this example already. We've looked at this region already. X squared plus y squared equals 8 is a circle of radius 2 square root of 2, and x equals 2 is a vertical line. So the region that's inside the circle and to the right of the line is going to be that region right there. Let's redraw the picture and just focus on that part of it. I'll make it a little bit larger. So the region looks something like that. This near edge is the line x equals 2, and the far edge is x squared plus y squared equals 8. Now in that previous video, we wrote down what the polar equations of these two lines were. Recall that x equals 2 had polar equation r equals 2 secant theta, and x squared plus y squared equals 8 had polar equation r equals 2 square root of 2. The other thing we found were the polar coordinates of these 2 points. At the top point, recall that theta was equal to pi over 4, and down here, theta was negative pi over 4. So I'm not claiming here that that's obvious, but we did do that about 2 videos ago. If you missed it, you might want to go back and watch those videos. So now using this information, let's see if we can set up and do this integral. First, the easy part. Remember that in polar coordinates, dA is always going to be r dr d theta, and x is always r cosine theta. So the differential and the integrand we've got. Now we need to worry about setting up the bounds. Now looking at this region, if I go outward from the origin, notice that my ray will enter on the line and exit on the circle, no matter which line I drew, no matter which ray I draw. I'm always entering the region on the line and exiting the region on the circle. So, with respect to r, I'm always going to start at r equals 2 secant theta, and I'm always going to stop at r equals 2 square root of 2. Now, as far as theta goes, we're going to have to go from the smallest value of theta in the region, which is negative pi over 4, to the largest value of theta in the region, which is pi over 4. So those are going to be the bounds. Cleaning this up just a little bit, that's the integral from negative pi over 4 to pi over 4 of the integral from 2 secant theta to 2 root 2 of r squared cosine theta dr d theta. Now you may think this is going to kind of knock itself out quickly like the previous two, because the integrand, once again, is the product of a function of r and a function of theta. Unfortunately, this bound right here is not a constant. Remember, we can only split this up as the product of two integrals when all 4 bounds are constants. So I'll have to integrate this out the slower way. First of all, we're going to integrate with respect to r, substitute the two bounds, and subtract. So integrating with respect to r, we have 1/3 r cubed times cosine theta, taken from r equals 2 secant theta to r equals 2 square root of 2. Let's plug in the two bounds and subtract. The 1/3, if I want, I can factor out in front. Plugging in r equals 2 square root of 2, add 2 root 2 cubed. 2 root 2 cubed is 8 times 2 square root of 2. So that's 16 square root of 2 times cosine theta minus, plugging in the lower bound, 2 secant theta cubed will be 8 secant cubed theta times cosine theta d theta. Let's simplify that a little bit. I have 1/3 in front. Inside, I have 16 square root of 2 cosine theta minus, remembering that secant is the reciprocal of cosine, if I take secant cubed times cosine, one of the secants will cancel with the cosine and just leave me with 8 secant squared theta. Oh, well, that's not going to be so bad to integrate. The integral of cosine is sine, and the integral of secant squared is tangent. So I have 1/3, the integral from negative pi over 4. Oops, I'm carrying out the integral. I have 1/3 times 16 root 2 sine theta minus 8 tangent theta, taken from negative pi over 4 to positive pi over 4. So let's plug in the endpoints and subtract. 1/3, 16 square root of 2. Sine of pi over 4 is 1 over square root of 2, minus 8 tangent. Tangent of pi over 4 is 1, minus 1/3 of 16 root 2. Sine of negative pi over 4 is negative 1 over square root of 2. Oops. Minus 8 times tangent of negative pi over 4 is negative 1. And let's come over here and finish it out. I have 1/3, the square roots of 2 cancel, 16 minus 8, minus 1/3 of negative 16 plus 8, which is 1/3 of 8 minus 1/3 of negative 8, which is 16 over 3. So the value of the integral is 16 over 3.